Chapter 8 Process Preventive Controls for Human Food, Parameters and Values, including Critical Limits, presented by David Rawson. Hazards requiring a process. Preventive control are determined and identified during the hazard analysis process. Per the regulation 21 CFR 117.13 5C1, process controls include procedures, practices, and processes to ensure control of parameters during operations, such as heat processing, acidifying, irradiating, and refrigerating foods. Process controls must include, as appropriate to the nature of the applicable control and its role in the facility's food safety system. 1. Parameters associated with the control of the hazard, and 2. The maximum or minimum value, or combination of values, to which any biological, chemical, or physical parameter must be controlled to significantly minimize or prevent a hazard, requiring a process control. Process preventive controls are frequently called critical control points, CCPs. A CCP is defined in the regulation as a point, step, or procedure in a food process at which a control can be applied and is essential to prevent or eliminate a food safety hazard or reduce such hazard to an acceptable level. See Appendix 8, Definitions. Once a process preventive control, such as a CCP, is identified for a specific hazard, parameters and values are established to control the hazards identified in the hazard analysis. Definition: Critical control point, CCP. A point, step, or procedure in a food process at which control can be applied and is essential to prevent or eliminate a food safety hazard or reduce such hazard to an acceptable level. 21 CFR 117.3. A variety of formats can be used to document process preventive control information. This course uses the format above, which includes information that must be documented in the food safety plan. This chapter focuses on establishing parameters and values, including critical limits. Chapter 9 focuses on determining, monitoring, and corrective action procedures. Chapter 10 focuses on verification and record-keeping activities. As illustrated in this example, the steps identified as requiring a process preventive control, including CCPs, along with the hazards requiring a preventive control, are transferred from the hazard analysis form to the first and second columns of the process preventive control form. This form may be referred to as a HACCP chart if desired. The food safety team determines and lists the parameters, values, or critical limits, the minimum or maximum values associated with the parameters, for the controls for each hazard, all elements of monitoring, any corrective actions to be taken when deviations from the critical limit occur, the verification procedures, and records in subsequent columns. This chapter discusses critical limits on the process preventive control form, elements of monitoring, corrective action, verification, and record-keeping requirements are addressed in separate chapters. Process preventive controls link back to HACCP principles that typically result in the identification of critical control points, CCPs, under 21 CFR Part 117. Process preventive controls are identified through a hazard analysis when specific hazards will be controlled by the given process step. Under HACCP, these process controls controlling the hazard would have been identified as CCPs. The term CCP is used generically for process preventive controls. For simplicity, the term critical limit is used in the rest of this chapter instead of minimum or maximum values associated with the parameters and values to control the hazard. Critical limits play an important role in a preventive control program. If a significant hazard exists, it is important to understand values for the parameters that must be met to control that hazard. This chapter focuses on how to establish science-based critical limits, which help to assure process preventive controls are effective. Sources of information on critical limits are readily available, and these will be discussed later in the chapter. The chapter also discusses different approaches used to establish a critical limit, as well as the advantages and disadvantages of these approaches. This chapter also covers operating limits, a more conservative limit, e.g. higher or lower temperatures than needed for safety, used in production to minimize the risk of not meeting a critical limit. Operating limits are often established for meeting quality standards. Finally, the chapter illustrates how to begin to complete a process preventive control form. For most process-related preventive controls, measurable parameters can be identified, and the values established for these parameters are called critical limits, as cited in the regulation in 21 CFR 117.135C1II. The critical limit must be met at the process control step, or CCP, to significantly minimize or prevent the hazard requiring a preventive control. If a critical limit is not met, the process control step is not in control, i.e., a deviation has occurred. When not in control, the potential for producing a product that presents a consumer health risk exists. Examples of parameters that may have critical limits established for control include cook time, temperature, flow rate, line speed, product bed depth, weight, viscosity, moisture level, water activity, salt concentration, pH, and others, depending upon the process. Because of the potential safety implications, meeting critical limits at a process preventive control is essential for the safety of the product. When critical limits are not met, predefined corrective actions must be taken. Basing the critical limit on instantaneous, real-time data will allow for better control of the process. The critical limit is generally expressed as a value equal to or above or below a critical value, and not at the specific value itself. For example, processing equipment may not easily maintain the exact value of 160 degrees Fahrenheit, 71 degrees Celsius, so the critical limit would be set at equal to or greater than 160 degrees Fahrenheit, 71 degrees Celsius. This allows the CCP to be achieved and gives the option of exceeding it to enable being more conservative or to operate at a higher processing limit. There frequently are different ways to control a specific hazard. The food safety team decides the best option for the particular CCP based on practical considerations, such as the process capabilities, how measurements can be made, staff capabilities and experience, and other appropriate factors. This may mean the chosen limit may not be available in the literature, but it still needs to be validated following sound research principles. A number of sources of scientific and technical information can be useful in establishing critical limits. The FDA and other governmental agencies may provide information through technical staff, regulations, guidelines, directives, performance standards, tolerances, and action levels. Trade associations, process authorities, industry scientists, university and extension scientists, expertise, and guidelines. Scientific studies for specific products can be conducted within a facility, at a contract laboratory, or at a university. Information can also be obtained from peer-reviewed scientific literature. Care must be taken when applying information from literature sources to critical limits for a specific product and process. There may be important differences between the methods used in a published study and those used for the product and process under consideration. The critical limits may need to be adjusted to account for those differences. For example, higher fat levels in a product may have a protective effect in the microbial lethality of a heat treatment for that product. A higher temperature or a longer time may be required to achieve the same level of lethality compared to a lower fat product. There are many different types of critical limits. Critical limits must be specific for the process preventive control step and the hazard that is being controlled. Different critical limits may be needed for ingredient-related hazards and process-related hazards. Each process preventive control must have one or more critical limit for each food safety hazard. An effective critical limit defines what can be measured or observed to demonstrate that the hazard is being controlled at that process preventive control step. For example, both time and temperature measurements may be elements of a critical limit to eliminate food safety hazards, such as pathogens, at a cook step. There can be multiple critical limits established for a single process preventive control based on different conditions that occur in the process. Facilities may have different parameter options for controlling a specific hazard. The selection of the best parameter is often driven by practicality and experience. Critical limits may involve multiple parameters, such as time and temperature and bed depth, for a nut roasting process, or free chlorine and pH in a produce flume wash water system. The nature of the product, the specific process, and the hazard being controlled influence what parameters may be used. Additionally, a facility may have different options for the critical limits to control a specific hazard. For example, a facility may choose to use a higher oven temperature and or a reduced bed depth in the peanut butter process to achieve the safety level of heat treatment more quickly. Parameter options and critical limits must be determined on a product by product basis and must consider the role of the specific process. Preventive control in relation to the food safety system. A variety of approaches could be applied to set critical limits for a cooking process. Preventive control, intended to eliminate the hazard of vegetative pathogens in a frozen omelet. In the example on the slide of the frozen omelet, it is a batch process where it is a measurement of product temperature. In this case, the product temperature achieved during cooking is set as the critical limit. However, the product temperature may not be easy to monitor for each individual product cooked. Heat transfer rates during cooking could also vary for several reasons. For a fluid product like a sauce, measuring the product temperature may be practical because the liquid could be mixed. For a solid product like an omelet, a procedure would need to be developed for consistently measuring the temperature of the omelet. If products are produced using a batch process, e.g., multiple products baked together in a set of pans, then product temperature may be workable as a critical limit. However, if each omelet is individually made, it may be less practical to measure and record temperature because the time needed to capture the data for each unit may be difficult, especially considering that doneness may vary from one omelet to the next. Batch processes are distinguished from continuous process in how the critical limits are measured. As an alternative to batch process for cooking the omelets, the E.G. Food Company could have used a continuous process where a critical limit is established for the process parameters. An example of how this could have been done is shown here. The reality is that except in limited circumstances, e.g., the product is a liquid, such as milk in a pipe or continuously stirred liquid product, it can be unpractical to continually monitor the temperature of each individual food product on a processing line to ensure conformance with a critical limit. As an alternative, the example above establishes process conditions necessary to ensure that the cooking process achieves the minimum product time and temperature. In this approach, the oven temperature, the belt speed going through the oven, and the volume of batter placed into standard pans are all factors that affect the consistency of the product's final temperature. These parameters are easy to monitor, and measurements are obtained quickly to determine that critical limits have been met. A scientific study, validation discussed below and in Chapter 10, verification and validation procedures must be performed to ensure that controlling these process parameters at the specified critical limits will always result in an internal product temperature that will destroy pathogens of concern. Typically, this option provides better assurance and may be easier to perform than the previous option, even though more parameters must be monitored at this step. Use of an operating limit allows the detection of a potential problem before a critical limit is not met. The value for the operating limit parameter is usually more stringent or conservative than the critical limit. Operating limits should not be confused with critical limits. Operating limits would be more stringent than the critical limits to ensure that the critical limits are not exceeded. A process may be adjusted when the operating limit is not met, which avoids deviating from the critical limit. These actions are called process adjustments. A processor may use these adjustments to avoid loss of a critical limit control, resulting in a process deviation and the subsequent requirement to take corrective action. Spotting a processing trend toward loss of control early and acting on it can save product rework or, worse yet, product destruction. Operating limits may be selected for various reasons. For quality reasons. For example, product may be heated to higher temperatures above the critical limit, set to eliminate pathogens in order to eliminate spoilage organisms with higher heat resistance. To avoid deviating from a critical limit. For example, a product that must be acidified to Pcqi 4.6 for safety may have a more stringent operating limit of 4.4 to reduce the likelihood of exceeding the critical limit. To account for normal variability. For example, a fryer with a 5 degree Fahrenheit, 2.8 degrees Celsius, variability should be set at least 5 degrees Fahrenheit, 2.8 degrees Celsius, above the critical limit to avoid violating it. Typically, operating limits are set by the processing plant based upon operating data taking process variability into account and often exceed regulatory requirements and recommendations, generally at values more conservative than the critical limits. The example on the slide demonstrates two important points. 1. Operating limit deviations and how they relate to process adjustments. And 2. Critical limit deviations and how they relate to corrective actions. In this example of a cooking process, a critical limit is established at 158 degrees Fahrenheit, 70 degrees Celsius, and the temperature fell below that limit. Setting an operating limit above the critical limit could have alerted line personnel to make a process adjustment to bring the cook temperature back above the operating limit. If an adjustment is made before the temperature drops below the critical limit, no corrective action record is required. However, in this example, an adjustment was not made until after the temperature dropped below the critical limit of 158 degrees Fahrenheit or 70 degrees Celsius. Thus, appropriate corrective actions must be taken, and a corrective action report must be written and included with preventive controls records. In this example, setting the operating limit more stringently than the critical limit allows for response by plant personnel before reaching the point at which there is a deviation that requires corrective actions. This example shows that the operating limit was set at 162 degrees Fahrenheit, 72 degrees Celsius, which is more than adequate to assure temperatures remain above the critical limit of 158 degrees Fahrenheit, 70 degrees Celsius. As previously discussed, the E.G. Food Company's critical limit for cooking the omelet was determined to be omelet surface temperature is greater than or equal to 158 degrees Fahrenheit or 70 degrees Celsius, instantaneous before transfer to assembly table. This information is recorded in the food safety plan. Critical limits, i.e., a maximum and/or minimum value to which a process effectively controls a food safety hazard to an acceptable level, must be determined for each process preventive control, e.g., CCPs, that has been identified in the hazard analysis. Process preventive control's critical limits must be validated to ensure that the values established are effective in controlling the hazard. Operating limits are set more stringently than the critical limits to ensure that the critical limits are not exceeded, considering specifics related to the process variability and product quality. You have completed the lecture for Chapter 8. Be sure to complete the knowledge check as well as the Chapter 8 exercise. See you in Chapter 9.